less than 10 seconds.
Hey everyone, Michael here from the Space Center, once again joined by Morgan from Let's Talk Science. Hey Morgan.
Hey Michael.
So this week, our theme is black holes, and I'm really excited about this theme. This is a topic that always sparks wonder from kids, the youngest ages, to the oldest adults. It's something that is so fascinating because it's so powerful in the universe. We can't see it, but it's out there, and it continues to fascinate us. And this week, you developed an activity to help us understand black holes.
Yeah, so this week we're looking at modeling the birth of a black hole or the death of a star. So when a star undergoes its end of life period, it can be called a supernova event, and it's one of the ways in which a black hole might form. There are others, but we focus on this one, and we go through a really fun activity where you just learn about how that happens up in the universe.
Awesome. And of course, you probably had a lot of questions as you were going through this process. What sort of wonders did you have about black holes?
You know, I love to nerd out. And so I came across this term that I didn't look too much into because you're a great explainer and I wanted you to explain it to me. And I learned that something can happen if a person or a thing goes into a black hole called spaghettification. And as a spaghetti lover, a lover of all food and carbs, as we've established,
Yeah.
I was hoping you could tell me more about that.
Yeah. So, I'm not too sure why this term came up. Of course, like trying to think of what would happen to a person next to a black hole is just like one of those thought experiments. Like it's never going to happen.
Yeah, has anybody ever fallen into a black hole?
No. Black holes are very far away, so we don't need to worry about that. So really what spaghettification is trying to think of trying to separate the event of the black hole from other types of like suction events that we might be familiar with. So, for instance, if you watch your toilet, the water sort of like spiral down or at the bottom of a drain, those are good analogies to have like give us like a basic framework of how gravity would pull something down. But with black holes, we're talking about the most powerful thing in the universe. Like gravity is pulling and squeezing everything. So basically what would happen is every single atom in your body would start to pull apart. And, like it would start with like your feet, and then slowly kind of like every little bit of your body would just sort of like start to like stretch out. And as you got closer to the black hole, this perhaps might be a very slow thing. So they started to imagine sort of like this very sort of like very long stretching action that would happen where basically every single atom in your body would just stretch out to infinity. You would die very quickly, but it would be, not good.
And so you look like a bunch of spaghetti noodles. Is that where the name came from?
Basically, yeah.
Interesting. But
Yeah.
it would happen so quickly that you would never actually see that, would you?
Well, exactly. I mean, you basically, if you're anywhere near a black hole, you're probably dead by the radiation. So it's really just sort of like a thought experiment anyway. We do sort of see time dilation effects, as you get close to a black hole. We saw that in Interstellar, where they went to Miller's planet, which was closer to a black hole. And so because of the gravitational effects on that planet were closer to the black hole, that meant time was slower than normally. So that when they went to the planet and they came back, everyone was aged. So even time stretches out. So you can also think of like time being spaghettified as well, as things get slower. So it kind of feels like we're in a black hole right now. Time seems to be stretching out.
Definitely.
Spaghettified. Awesome. Well, let's get to this week's activity. I'm really excited to get going with it.
Yes, let's do it. Enjoy, everybody.
Have fun.
This week we are learning all about black holes and how they are formed in space. Like we mentioned in the gravity episode, black holes are an immense form of mass that are out in space that have such a huge force of gravity associated with them that once captured, not even light can escape. This has caused astronauts to develop ways to observe black holes indirectly and has led us to ask many questions about these unusual space formations. Black holes can be formed in one of many ways, one of which includes the end of a star's life, or a supernova event. At the center of the star, a burning core exists, where nuclear fusion occurs and joins lighter elements together to form heavier elements. This process generates heat, exerting an outward pressure, counteracting the force of gravity that pulls the gas towards the center of the star. Stars spend most of their lives with these two forces in balance, maintaining its shape and size. You can visualize this process with a hot air balloon that needs the flame to keep the balloon inflated and floating. If the flame goes out, the balloon will collapse and fall from the sky because there is no more hot air to keep the balloon inflated. All stars start out fusing hydrogen into helium. Small cool stars will stop soon after that and will not continue to fuse any other heavier elements. This very hot and more massive star can continue this fusing process to create even more massive elements, not only burning hydrogen and helium, but other elements like carbon, oxygen, and silicon. As the star reaches the end of its life, the nuclear fusion forms iron. Iron is a very stable element and does not easily fuse into heavier elements. Therefore, it requires more energy to fuse than it can produce. So the iron core doesn't fuse into further elements, and the star stops producing energy. When the energy production stops, the force of gravity can finally overcome the outward push from the energy generated by the fusion. As a result, the heavy outer layers of gas of the star are unsupported, and the star's core collapses. In the resulting implosion, the rest of the star is blown apart. The explosion of a star is called a supernova event. All massive stars will end up this way at the end of their lives, but only the most massive of them will form a black hole. To model the formation of a black hole, we're going to do a simple activity where we look at the death of a star using a balloon and some tinfoil. And you'll also need, in order to simulate the death of the star, a sharp pin and a weighing scale if you have one available to you. So you're going to take your balloon and blow it to be about the size of a small watermelon. This is going to form a part of the burning core of our star. Once you've gotten your balloon blown up, you're next going to take a piece of your tin foil and wrap it around the balloon. This first layer of foil and the balloon together form the burning core of the star. Next, we're going to take a second layer of our tinfoil to wrap around our burning core to simulate a layer of gas that is held to the surface of the star by its force of gravity. In order to see how the weight of a star might change before and after a supernova event, we're going to take the initial weight of our star and its surrounding layer of gas and compare it after the supernova event to its weight then. So the initial weight of the star and its surrounding layer of gas is about 9 grams. We'll record that in our lab notebook. Now we take our pin and we simulate the supernova event simply by penetrating our external layer of gas surrounding our burning core and the balloon, the burning core itself, to pop the balloon. Once the core, the burning core of the star has stopped burning, it no longer has a force to keep the outer layer of gas pulled toward its center. So we're going to remove the outer layer of the foil from the burning core of the star, and we're going to simply blow this away as it would in space. Now, with our burning core, we are going to cause it to further compress just by squishing the ball and the popped balloon down into a smaller ball than what we started with. This occurs in space because there is no longer the pressure being generated by the burning core of the star counterbalancing the force of the gravity that's acting on it. And so it compresses in space into a smaller ball. We are left with something like this. Again, we are going to take the weight of this imploded star, and we see now that it only weighs 5 grams. So we're going to move this to the side again, make that recording in our lab notebook. So what about its density? If we have a smaller volume with less mass, how do you think the density of the star compares to the star before the supernova event, which was larger and had more mass? Let's see. Density depends on both volume and weight, or mass, which can be reflected by its weight. And when we have more mass spread over a larger volume, something tends to be less dense than when we even have a smaller amount of mass in a more compact space, depending, of course, on how much the volume of the object changed. After their formation, stellar mass black holes can continue to grow as they accumulate more matter from their surroundings, such as other stars, gas, and other black holes. If a black hole absorbs enough material, it can even grow to be more massive than 1 million suns. These extremely massive black holes are called supermassive black holes, very logically so, and are the largest of them that we are aware. Supermassive black holes exist at the centers of most galaxies. One even exists at the center of the galaxy that we live in, the Milky Way. It's believed that in the conditions of the early universe, there were a lot of large, short-lived stars. Therefore, many stellar mass black holes may have existed, which then gradually accumulated material and merged together over time. Black holes that have a mass in between the stellar and supermassive black holes are referred to as intermediate mass black holes. Theoretically, these black holes should exist, but we haven't found any in space yet. Black holes are much smaller than we might expect them to be based on how much mass they can hold within them. Albert Einstein's more nuanced definition of gravity describes gravity as a space curvature that is caused by some sort of mass or some sort of body out in space. Therefore, we can say that black holes have a massive amount of space curvature associated with them that traps other objects that get within their vicinity and does not allow them to escape past a certain point. Again, light can't even escape from these space formations because of the massive amount of gravity that they have associated with them, which is why it is so important for us to observe the motion of other celestial or space bodies relative to these black holes. That is all for this week. We hope that you enjoyed modeling your very own death of a star or birth of a black hole, and you comment in the section below about what you think of the density of black holes or the density of stars before their formation and how they compare to each other, as well as some of the other questions that we have put in the reflections in the attached instructables associated with this video. Thank you guys so much for tuning in, and we'll see you next week.